Alright, so we have our function that we're trying to optimize. So we have our Jacobian, but we need to evaluate the Jacobian at each new value of x. But this is time consuming, especially in Python, so we use the Broyden method. So here we see that our new function is approximately our previous function plus the Jacobian times the change in x that we took. Let's say we set it to 0 because do this. Because if the Jacobian was correct, and f is linear, then f plus the Jacobian times the delta x would equal 0. But we know that this doesn't work. We know that, but we do know that delta x is our new value minus the previous value of x. We can write that down. Alright, and now if we evaluate at this new point, x plus, we get information about the function and the Jacobian. So the previous Jacobian wasn't correct, which we know here. So we can set up a new equation for f plus, which will be our previous function plus our new Jacobian times that change in x that we took, with j plus being our new Jacobian, like I said, that when multiplied by delta x gives the correct value of our new function f plus that is not 0. Alright, and then we want to solve for that new Jacobian. Okay, so we have two equations. If we bring this down here, alright, and then if we subtract these two, we get what we would call our change in the Jacobian. We get plus equal to, those cancel out. We have our new Jacobian minus our previous, which gives us the change in the Jacobian times delta x. Alright. Now we have a relation between our new function, f plus, and the change in the Jacobian, but this will not give us the answer because the Jacobian has too many unknowns, so we need another statement. So we know that if we move from some point x, draw this over here, let's say this is our first value x, and then our function with respect to that, and then here is our new value x plus, and the corresponding function. We know that our equations tell us that as we take this step, our new function equals the change in the Jacobian plus or times the change in our x values. But if we move in a direction perpendicular to delta x here, let's say, some arbitrary vector y, where y is perpendicular to delta x. I know that's not perfect, but we'll say that y is perpendicular to delta x. This movement in the direction y has no effect on the Jacobian, and j plus y equals previous y, or previous Jacobian times y, because with this movement we know no new information about our new function. So now we can write this set of two equations. I'm going to go change the Jacobian, delta x, it's our new function, and also the change in the Jacobian y direction equals 0. Because like I said, when we move in this direction perpendicular to the change in x, we get no new information. Therefore, it has no effect on the Jacobian, like we see here. So it equals 0. Alright, so I'm going to start a new, we'll clear, and then I'll rewrite those two equations that we just derived. And this, like we showed with that diagram, is only true when y is perpendicular to that change in x, and therefore their dot product would be 0. So then we can combine those two equations. Right. And then additionally, we can write that our change in the Jacobian times y y x, or delta x, over the norm, or delta x times delta x, oops, which satisfies this set of equations here, where delta x times delta x is the norm, or the length of the vector squared. But delta x and y here are n by 1 matrices, so we need to take the transpose of delta x. And we can do so by, and then we can do matrix multiplication between a 1 by n matrix and an n by 1 matrix. So then we'd get, bring this up here, delta x transpose y over delta x and norm of it. And you know what I forgot? I completely forgot to bring this function, our new function down. Important. So that's just multiplied out here. Okay. And then if we bring this y out and our f plus over here, it equates to y. Alright, and then now we see if we divide both sides by y, we get the change in our Jacobian. Alright, and then we have simple matrix multiplication here, and then the norm of delta x is just a scalar. So, but if we remember that equation where f plus the Jacobian times delta x is equal to 0, and we solve for x plus, I'm gonna go ahead and clear again. Alright, so as I was saying, if we look at 0 equals and we solve for x plus, knowing that delta x equals our new x minus our previous value of x, we get negative f equals the Jacobian plus and then ultimately if we take the inverse of the Jacobian on each side, we get x plus equals x minus f times the inverse of the Jacobian. So what we'll see in our code to get our next x value, our x plus, we'll have to take the inverse of the Jacobian each time we update it, which is a very hard evaluation and it's very time consuming in Python. So in the next video, we'll see how you can employ the Sherman-Morrison formula, which is here, to easily compute the inverse of the Jacobian, which we'll have to do at each update, and then its corrections following a rank 1 perturbation.